Hello friends, welcome to this lecture. And here if you recall, we have discussed the functional and the curves which minimizes the functional. And now in this lecture what we try to do here, we consider the functional which depend on the surfaces, and here we want to find out the equation in terms of surfaces which minimizes the functional. So here we want to find out, say, extremal, which are surfaces which minimizes the given functional. So let us discuss here. So in this lecture we will study the problem of finding the extrema of functional involving multiple integrals leading to one or more partial differential equation, and we can consider our functional as this g of z of x y, which is double integral f of x comma y z z of x z y over a region of integration d by determining z which is continuous and has continuous derivative up to the second order. So here we want to minimize this functional. So here please remember, here the minimizer of this functional is your z of x y, which is not a curve but a surface, right. So if so far we have discussed the cases where the minimizer of a functional is only a curve, but here we want to find out, say, minimizer or say extremizer of a functional which is nothing but a surface in place of a curve. So here this D represent the domain on which this surface is defined here, and we say that this domain D is bounded by the boundary C, and the value of Z on the boundary C is given by some initial condition. In this case we can call this as boundary condition, and here we have we assume that this integrand f is at least 2 times differentiable, or we can without any problem we simply assume that f is 3 times differentiable, but I think only 2 time differentiability is required here. So here what we want to know, we want to find out, say, Euler kind of condition. So here we proceed in a same way as we have proceeded for the curves when extremals are nothing but curves. So here also let us assume that the extremizing surface is z equal to z of x y. So as you remember, we have already seen that with respect to this extremizing surface we define a one parameter family of surfaces as z of x y alpha equal to z of x comma y plus alpha delta z, where this delta z is a variation in with respect to z here. So let us take z1 xy is another surfaces which is arbitrary but fixed. Arbitrary in the sense that you can take any surface having the same boundary condition as z has a boundary condition, and fixed in the sense that you can take any surfaces, but once you take this surface then it is fixed. So here delta z is nothing but z1 xy x comma y minus z x comma y. Here we may also call this z1 x comma y as a admissible surface for the extremal J, right. So here z1 and z both satisfy the same boundary condition on the boundary of the domain D C. So here we want to as we have pointed out that the condition that the for the extremal of the functional the variation has to vanish, and that theorem is not depending on the form of the functional. So if it is true for the functional for which your minimizer is or extremizer is your curve, so it is also true for the this case also, where the extremizer is nothing but surfaces. So here the necessary condition for an extremum is the vanishing of the first variation. So first variation here is z of x comma y comma alpha equal to z of x comma y plus alpha delta z. Here to be noted here that by suitable choice of alpha and z1 you can find out any surface having the same boundary condition between, say, same boundary condition on the boundary C by suitable choice of z1 and alpha. So zx comma y comma alpha is given by this, will represent any arbitrary surface having the same boundary condition. And not only this, if you look at your alpha equal to 0, then this this one parameter family is reduces to z of xy, which is the minimizer, which is the extremizer of the functional here. So here we can say that on function of the family z of x comma y comma alpha, the functional z reduces to a function of alpha. So here delta z is fixed, zyx is zxy is already given as extremizing surface. Delta z is fixed because z1 is arbitrary, but once it is taken, it is fixed. So here delta z is also fixed. So the only varying quantity is your alpha. So you can say that zx comma y comma alpha is nothing but a function of alpha, and hence your functional is reduces to a function of a alpha. So here in the same way we can say that that extrema will occur at alpha equal to 0, and hence you can say that double by double alpha j of zx x comma y comma alpha is equal to 0 at alpha equal to 0. So to find out this, this we denote as double j. So double j is equal to double by double alpha, and you write down the functional j of zx comma y comma alpha. So it means that define your j as for this one parameter family of surfaces z of x comma y comma alpha. So here you can write j of this as f of x comma y. In place of zxy, now I am writing zx comma y comma alpha, and here zx can be written as notational, you can write it px comma y comma alpha, and comma zy is written as q of x comma y comma alpha, and we want to find out, say, derivative of this with respect to alpha at alpha equal to 0. So let me write it here. Your delta z is equal to double by double alpha, and now j of j of z of x comma y comma alpha. Here you can write z comma x comma y comma alpha. So here you can write it at alpha equal to 0. So here you can write it double by double alpha, and this is double derivative on d, and here you can write it f. So x comma y is already zx comma y comma alpha and z of x. So here when you write z of x x comma y comma alpha and z of y x comma y comma alpha, and that is with respect to this integral is with respect to dx and dy. So here this we denote as pxy alpha, and this we denote as q of x comma y comma alpha. So when you find out, say, derivative with respect to alpha, then you will get this is as d, and here f x y. Now here this is what this is independent, this is depending on alpha, this depending on alpha. So here this so by using the formula of derivative, you can simply say that it is double by double alpha of this quantity is given as f with respect to z x comma y comma alpha, and double of z x comma y comma alpha, double z x comma y comma alpha double alpha plus f of p here, and double p x comma y comma alpha upon double alpha, and f of q and double q x comma y comma alpha double alpha, right? And here this is dx and dy, and at alpha equal to 0. So here if you write down what is z of x comma y comma alpha, so x comma y comma alpha is equal to z x of y plus alpha delta z, right? So alpha delta z, this is delta z. So when you find out say derivative of this zx comma y comma alpha with respect to alpha, and at put alpha equal to 0, you will get that del z x comma y comma alpha upon del alpha, it is coming out to be delta z. So at alpha equal to 0 also it is coming out to be delta z. So this is reduces to delta z, and similarly when you find out say derivative of this with respect to del alpha, you will see what when you differentiate with respect to x, you will get what it is zx x comma y comma alpha equal to zx x comma y plus alpha delta zx, and when you differentiate with respect to alpha, you will get del zx x comma y comma alpha del alpha is equal to your delta z of x here. So at alpha equal to 0 also you will get the same thing, because it is not involving any alpha, so it is your delta z of x, so which we call this as delta p here. So similarly you can calculate the derivative here at alpha equal to 0, and it is coming out to be delta q here. So let me write it here. So here we can write it that variation of the functional, you can write it fz delta z plus fp delta p plus fq delta q dx dy, where delta p and f this pxy alpha is related by this. So px comma y comma alpha is equal to del z x y comma y comma alpha with respect to del of x, that we have already defined, and it is coming out to be px comma y plus alpha delta p. Similarly you can define qx comma y comma alpha, which is the derivative of z x comma y comma alpha with respect to y, and it is given as qxy plus alpha delta q. So when you differentiate with respect to alpha, you will get here as delta p and delta q. So now so delta z is equal to 0 means this double integral is going out to be 0 here. Now the problem is that we do not want this term delta p and delta q, because we want everything in terms of z only. So what we try to do here is then we try to simplify these two terms, and for simplifying these two terms, here we use this relation that del by del x of fp delta z is equal to del by del x of fp delta z plus fp del z by delta z by del x. So here you can say, using the chain rule kind thing, you can write it like this: del by del x of fp delta z is equal to del by del x fp delta z plus fp delta p. Similarly you can define del by del y of fq delta z, which is given by this. What we want is this thing, that integral of fp delta p plus fq delta q, which is here. So here you can say that the value of fp delta p plus fq delta q is equal to this summation minus this summation. So you can write it that integral double integral fp delta p plus fq delta q dx dy is given as double integral del by del x of fp delta z plus del by del y fq delta z, that is summation of this minus summation of this, that is minus del by del x of fp plus del by del y of fq delta z dx dy. So here we can simplify, or we can say that in this integral which is coming out to be 0, we are trying to find out say value of this integral in terms of delta z delta x delta z dx and dy. So here this is coming out to be this difference of these two integral, and for simplifying these two integral, let us apply say Green's theorem for the first integral. So if you remember, the Green function theorem is Green's theorem is double derivative del nx plus del n by del x plus del m by del y dx dy is equal to c n dy minus m dx. So here d is the domain bounded by the curve c. So it means that here the integral on the domain is reduced to the integral on the boundary of this. So here if you recall, then here n is going to be fp delta z and m is going to be fq delta z. So using this Green's theorem, you can write it n is fp delta z. So here fp delta z dy minus fq delta z d of x. So now this is coming out to be 0. Why? Because delta z is what? Delta z is the difference of z1 xy minus z1 xy and z of xy, and both z1 xy and zxy satisfy the same boundary condition on the boundary C. So it means that the delta z, which is the difference between z1 and z, is satisfying the delta z has to be 0 on the boundary. So using this fact, you can say that this integral is coming out to be 0, which is nothing but this double integral. So it means that the first term in this case in this is coming out to be 0. I cannot apply the same theorem for this second integral, because here this will reduce to your fp dy minus fq dx, but delta z is not there. So here we may not apply this thing. So here we simply say that first integral is coming out to be 0, and using this we can simplify our integral, double integral fp delta p plus fq delta q dx dy is equal to integral on d double by double x of fp plus double by y fq delta z dx dy. So here the equation that total variation is 0 is reduced to this integral, that double integral fz delta z plus fp delta p plus fq delta q dx dy is now reduced to this form. So here fp delta p, this here we are utilizing this equality. So using this equality, you can write that the second and third term can be replaced by this. So here you can say that double integral fz minus double by double x of fp minus double by double y fq delta z dx dy is equal to 0. So here if you look at, since we have assumed that f is thrice differentiable, or you can say f is second derivative of f is continuous. So you can say that this is a continuous function. Now look at this part, delta z. So delta z is basically a continuous function. In fact, it is also a differentiable function. So here we can say that delta z is equal to 0 on the boundary, and having continuous having first and second order derivative continuous on the domain D. So here, to get some information about this quantity, we use the generalization of a lemma, which we have discussed for in the case of curves. So here let us consider what is this lemma. It says that if axy is a fixed continuous function in a closed region D, and if this integral, this double integral axy hxy dx dy is equal to 0, means vanishes for every function hxy which has continuous first and second order derivative in domain D, and equals to 0 on the boundary, then axy is equal to 0 everywhere in D. If you remember, if you recall, here hxy is your delta z. So here delta z is vanishing on the boundary, because it is it is the difference of two admissible curve z1 xy and the extremal surface zxy, both satisfy the same boundary condition. So delta z is going to vanish on the boundary, and it is arbitrary in the sense because z1 is arbitrary surface in the neighborhood of z. So you can say that if we take this lemma as true, then we can say that the axy, which is this quantity, has to be 0 on this thing. So for this, to prove this, we may generalize the concept produced in previous lectures. So here we want to see how we can easily prove. So here our claim is that if xy is a fixed continuous function and h is the function which whose first and second order derivative is continuous and on the domain D, and it vanishes on the boundary of the domain D, then this axy is coming out to be ideally equal to 0 function. So claim is that axy is ideally equal to 0. So here suppose it is not true, that axy is non-zero function, so it is taking say non-zero value. So let us assume without loss of generality that xy is say positive on, let us say strictly positive on some kind of a small sphere. So you can write it domain is as x minus x naught whole square plus y minus y naught whole square less than or equal to say epsilon square. So here what we can take, here we can take a closed ball around x naught y naught with the radius epsilon, and we say that your axy is taking the positive value on this small domain in and epsilon is small enough such that this domain is lying inside your D. Now we can choose our hxy in a way such that you can write it hxy as x minus x naught whole square plus y minus y naught whole square minus epsilon square and whole square. So by taking this, you can take hxy as this when xy lying inside your domain, let us call this as domain as x naught y naught with radius epsilon. So you can define it domain like this. So when xy belongs to this domain and epsilon x naught y naught, then your hxy is this, otherwise 0. So in this case, if we take hxy like this, then hxy will be 0 on the boundary, and it satisfies the condition that the first and second order derivative is continuous. So here the hxy satisfy all the assumption of the lemma, and also that the hxy and product axy, both product is going to be positive on this small neighborhood around x naught y naught with the radius epsilon. And in this case, if you find out the integral here, then integral on this n epsilon x naught y naught is going to be positive. Dx dy is going to be positive. So this is a contradiction here, because we have assumed that this integral is nothing but 0. So it means that the assumption that axy is positive in some domain is not correct, and hence your axy has to be 0. So using this lemma, you can say that since the variation delta z is arbitrary and the first factor is continuous, it follows from this lemma that the on the extremizing surface z equal to zxy, this equation, which is a second order partial differential equation, is has to be 0. So fz minus del by del x fp minus del by del y fq is ideally equal to 0, and with the so it means that the extremizing surface will be a solution of this equation along with the boundary condition which z equal to zxy takes on the boundary C. So this second order partial differential equation that must be satisfied by the extremizing function zxy is called the Ostrogradsky equation. So let us discuss example based on this. So first example is the minimize the extremal g of zxy, which is given by this double integral del z by del x whole square plus del z by del y whole square dx dy. So here functional is this g of z of x comma y is equal to double integral d del z by del x whole square plus del z by del y whole square dx dy with the condition that zxy take some value, say some value say g on say C, which is a boundary of domain D. So when you find out say Euler-Ostrogradsky equation for this, it is coming out to be, so here you can write it here as del f by del z minus you can write it here as del by del x of f of p minus del by del y of f of q, where p and q is basically zx. So here p is your zx and q is zy, or here you can say that your is equal to 0. So here f of x comma y z p and q is given I. If you look at this is nothing but p square plus q square. So this is Euler-Ostrogradsky equation, and you can see that there is no component of z here. So you can simply find out that minus del by del x here it is nothing but when you differentiate it is 2p, so double by z double x minus double by double y and 2 of double by, so double z by, so double z by double y is equal to 0. When you simplify this, you 2 you can 2 minus 2 you can take it out, and you can say that it is nothing but double 2z by double x square plus double 2z by double y square is equal to 0. So extremal surface must satisfy this equation, and if you recall, this equation is nothing but Laplace equation. So extremal surface is the solution of the Laplace equation when z satisfy certain condition on some boundary of the domain D. So you can simply say that, if you recall, this is nothing but your Dirichlet problem for the Laplace equation. So here we can say that the Euler-Ostrogradsky equation for this functional is coming out to be the Laplace equation. So we have to find a solution continuous in D of this equation that takes on specified values on the boundary. We have given that zxy is equal to z on the boundary, and this is one of the basic problem of mathematical physics, and which is known as Dirichlet problem. Here one thing to be noted here, that what we started with is to minimizing the variational or minimizing the functional given in this form, and it is coming out to be that the minimizer of this functional is coming out to be the solution of the Dirichlet problem. So and solution of the Dirichlet problem is the twice differentiable function, but twice differentiable function which satisfy this equation, but the solution of this is coming out to be the minimizer of this variational. So this observation is very important, and it help us to give a new direction to a new field which is known as the way of how to define a solution in a generalized sense, and this will give rise to to define a generalized solution in terms of distribution. So right now we are not discussing about that problem. So here we simply say that if we have a function like this, then the minimizer or extremizer is given by this Laplace equation with the condition that zxy satisfies some specified values on the boundary, and hence we can say that the extremizer of this problem is nothing but the solution of the Dirichlet problem. Now moving on to the next example. Here we have a functional double integral double z by double x square whole square plus double z by double y whole square plus 2z fxy dx dy. Now in a same way we can find out Euler-Ostrogradsky equation as double 2z by double x square plus double 2z by double y square equal to f of xy. So here if you look at what is the difference here between this first example and second example, in the second example we have added this term 2z f of xy. So if you use the Euler-Ostrogradsky equation, then this term is also present there. So when you simplify the contribution with respect to this is going to be 2 of f of xy, and rest it is same. So you can get that in second example we have this this thing minus 2 double 2z by double x square minus 2 double 2z by double y square is equal to 0. So you can simplify this as double 2z by double x square plus double 2z by double y square is equal to f of xy, and here your z of xy is equal to g on your curve C. Is it okay? So this is in D and this is on this side. So if you look at this is a non-homogeneous Dirichlet problem. So the solution, or you can say the extremizer of the functional given here z equal to z of, j of z of xy is equal to this. The extremizer of this must satisfy the Poisson equation, and this is also one of the very most studied problem in the physics, mathematical physics, and you can say that the solution of this extremizer, solution of this the extremizer of this functional is nothing but the solution of the Poisson equation. So in example 3 we want to find out a surface of minimal area stressed over a given contour C. So here we have a contour C and we want to find out a surface which gives the minimal area, and it is a generalization of the problem having the minimum surface area in one dimension. So here your functional is coming out to be s z of xy, which is given as double integral under root 1 plus zx whole square plus zy whole square dx dy. And in a same way you can find out say Ostrogradsky equation. If you remember, here integrand is not involving function z. So here you can simplify the Euler-Ostrogradsky equation, which is given by double x of p upon under root 1 plus p square plus q square plus double y of q upon 1 plus p square plus q square, and it is given as 0, and when you simplify it is coming out to be that zxx 1 plus zy whole square minus 2 zx zy zxy plus zyy within bracket 1 plus zx square equal to 0. So here in mathematical physics this surface, the solution of this differential equation represent a surface whose mean curvature is 0. So it means that this is the surface at which every point the mean curvature is 0, and we know that the soap bubbles stressed on a given contour C are surfaces having mean curvature as 0, and these kind of surfaces are known as minimal surfaces. So here we can say that the solution of these problems which minimizes this functional are known as minimal surfaces, and it satisfies the partial differential equation given by this one. So here we stop our discussion, and in next class we will see in the continuation of this, and in next problem we will see how to define how to take say example based on this, which is known as isoparametric problem. Some more example based on this Laplace equation we will discuss, that is isoparametric problem, and we also discuss the functional derivative and invariance of Laplace equation in next lecture. Thank you very much for listening us. We will meet in a next lecture.